Okay, so today we are going to look at the hypergeometric distribution. So this is a little bit different distribution because now we have a population, so you know exactly how many elements does this population has. If you remember, in the binomial distribution, the only thing that you knew was the sample, the number of elements. Now you also have this number of elements, this n, the sample size. However, you also know this capital N, that it's the population, the total number of elements. From that population, you have R, that are the elements with the desired characteristic in the population. So R and capital N are related. These are what you already know. No? You know the size of the population and you know how many elements are a success in that capital N. And then you select a sample of n elements, and from that you look for the number of elements with a desired characteristic in the sample. So as you can see, the small n and the y are related. So if you take a look, it's like, okay, you have this whole elements capital N, the total population. And then from that, you have some with the desired characteristic, R. And there are some others with another characteristic that you don't care about. And you are going to select a sample, a random sample. So this is n. And then you are going to count how many you have with the characteristic, how many of those in the sample size actually have the desired characteristic that you think as a success. So this is the formula here. This is a hypergeometric distribution. If you see, those here are combinations. This is a combination, this also is a combination, and this is a combination. So you are talking about counting tools. We look at this a couple of weeks ago, and if you remember, well, the notation is like this. In your calculator, you will look for this. Now the combination of RCY, or another way to write it is like this, or like in the formula here of the distribution. So you have three combinations. Those are multiplying. R, if you remember, is the number of successes that you have in the total population, and then y is the variable that you want to analyze, how many successes in that sample. In the denominator, this is the total number of options that you have. As a population of capital N elements, you select small n. And then, since these here are the ways that you can get y elements with the characteristic, this part here, the other combination here, are the rest. So everything that it's not in the first combination is in the second. So that's why, for example, you can see that this part, this one here, is the difference between the total minus the ones that have the characteristic. And the other part, the ones with the ones in the bottom, are also this part here, are the rest of the sample size. So you have n, small n elements in the sample, and from those that are not y, well, that's the rest of them. So that's the definition for the distribution. It's important to see here that you have these constraints. Y should be less or equal than R. And also you have these constraints, and actually it should make sense, no, since y is the number of elements with the characteristic that you want, it cannot be more than r, that are the total number of elements in the population with that characteristic. And the same goes with the other part, no, these are the first one, these are the ones within the sample, and these are the total. So the ones within the sample cannot be greater than the ones in the total population. So those are the characteristics of the distribution. As you remember, we also look at the mean and the variance. So that is the formula of the mean, a small n, that is the sample size, times r, that are the number of elements with a characteristic in the population, divided by capital N. And well, you have the variance there, that it's some products. These are products. This one, and this one are products. They are not combinations. So this is just R divided by N and so on. It's important for you to notice that you will look for the capital N in the problem. So that is actually the greatest difference with the binomial distribution. In the binomial distribution, we assume that the population was really, really big. So it doesn't matter the size of the population. The probability was constant from trial to trial. Now that's not the case, because since you have a population that with a size, a capital N, then it's not the same if you have already selected 5 defectives than if you have selected 10, no, and that's the total number of defectives in the population. So the problems that you are going to see, you are going to identify the three components: capital N, small n, and r. So those are the parameters for the hypergeometric distribution. So let's take a look at one problem. You have an urn contains 10 marbles, of which 5 are green, 2 are blue, and 3 are red. Then you select 3 marbles, one at a time without replacement. This means that you select one and you keep it out, so you don't return the marble to the urn. What is the probability that all 3 marbles drawn will be green? So let's find the 3 elements that we need for the hypergeometric distribution. Those are capital N. So this is the total population. You see here that you have 10 marbles. So capital N, it's 10. Then you should look for small n, how many you select from that population. And you see here 3. So small n is 3. Now let's define y. We want the probability that all 3 marbles will be green. So this is number, y should be number of green marbles. In the sample. So if you want y to be green marbles, then r should be the total number of green marbles in the urn, and those are 5. So again, you should remember that this y should match the r. If you define y as the number of blue marbles, then r is the total number of blue marbles in the population. And now you want the probability that y equals 3. Exactly 3. 3 marbles are drawn within the sample. So we have 3 combinations. The one in the denominator is the total number of combinations, selecting 3 elements out of 10. And then in the first one, you say how many successes, how many elements you have, and how many you want to select. In this case, well, this is the number, no? Y equals 3. And then in the other part, you write whatever is left. Since you have 10 elements in total and R is 5, well, the rest of them should be also 5. And then from the sample, you have 3, you want 3 greens, so you don't want to select any other element from the other group. So look at this. These elements here should add 10. And these elements here should add 3. Those, the 10 and the 3, are the ones in the denominator, the total. So now the only thing that it's left for you to do is to do this operation. So if you do the math, the result should be 0.083. And that would be the probability that from the sample of size 3, you actually get 3 green marbles. So let's do one more. It says here that you have used photocopy machines that are returned to the supplier, cleaned, and then sent back out on lease agreements. Major repairs are not made. However, as a result, some customers receive malfunctioning machines. Among 8 used photocopiers available today, 3 are malfunctioning. A customer wants to lease 4 machines immediately. To meet the customer's deadline, 4 of the 8 are randomly selected. So again, you should look for the 3 characteristics. Capital N, so this is the total number of elements. This would be 8 used photocopiers. That's capital N. And then you look for the sample, how many you select. So you select 4 machines out of the 8 machines, so this is 4. And now let's think about the number for Y. So Y, if you define Y as malfunctioning, machines, then R should be the total number of malfunctioning machines among the 8. And it says there that you have 3. And now let's use the formula. So letter A is no malfunctioning machine, so you want Y equals 0. Again, the formula says you have 3 combinations here. The one in the denominator is 4 out of 8. Then you have from 3 we want 0, and from the rest we want 4. So we want 4 out of the 5 that are right. So that would be the probability of no malfunctioning machines. Then for letter B, we want at least 1, so this would be greater or equal than 1. You can do Y equals 1 plus Y equals 2 plus Y equals 3. And that's it, because R is 3. Or you can do the complement, Y equals 0, that you already have this one. So probably it's better if you do it this way. Okay, let's do this. This is the last exercise. You have 5 cards that are dealt at random without replacement from a standard deck of 52 cards. What is the probability that the hand contains all 4 aces if it is known that it contains at least 3? So again, you look for the parameters of the binomial. So you have total number of elements, 52. Then you are going to select 5 cards, and then we want Y to be the number of aces. if you look at this probability, this is, you want the probability that having all 4 aces, and you already know that you have at least 3. So this is a conditional probability. You want the probability that y equals 4, exactly the 4 aces, given that you already know that y is greater or equal than 3. So if you remember the definition for conditional, in the numerator you have the intersection, and in the denominator you have the probability of what it's given. So if you want to be y equals 4 and y greater or equal than 3, actually the only possible way to get both is with y equals 4. And you have here y greater or equal than 3. You can think about these two, and I'm going to write it here. So you want y equals 4, and the other option is y equals 3 and y equals 4. This is the first part and this is the second part. So actually the only element that satisfies both is this one. And now both of them are just a operation with the hypergeometric distribution. So if I want y equals 4, I want from the R, that it's 4, I want to select the 4 of them, and then from the rest, that it's 52 minus 4, we want to select 0. And in the denominator, this is 52 and 4. So this is the first probability. And then the second one, this is y greater or equal than 3. So this should be y equals 3 plus y equals 4. So y equals 3, this is from the 4 aces, I want 3. And then from the rest, I want to select 1. And then divided by 52 combination 4. And then plus the result of the previous one. This is 0.123456. And the total here is 0.00071.